Welcome back, everybody. I hope you had a great start of the week. So today and tomorrow, we are going to follow up the discussion which we had last week about the singular value decomposition and interpretations of lasso and ridge regression, which are some of the methods which you will practice in project number 1. Tomorrow, we're also going to dive into a link with statistics and how we can interpret ridge and lasso regression. And many of the things which we're going to see now are going to be a little bit repeat of last week, but then my hope is that you can see the wood for the trees when you get these different interpretations, in particular when we use what's called the singular value decomposition. So I want to give you some of the mathematics behind these methods, because that hopefully gives a deeper understanding of what they are about and what are their advantages, their pros and cons, and so forth. So we actually want to demystify in this course many of the black box features of many of these machine learning algorithms. However, I wanted to start the lecture with some practicalities. And one of the practicalities is actually about the project and some discussions around where you find information on how to write the report and so on. And I've updated the project file because there was a leftover from last year where we actually didn't want people to write this as a scientific report, but we realized that last year that created more confusion than needed. So we actually reverted back to writing a normal report. Now, as I said at the beginning of the course, I mean, this is more meant as a way to give you a training in writing a scientific report. So one thing you're going to see is that in many of these calculations, you're going to generate tons of images, tons of results. In the report, it's actually you who tells the story. So you have to find a red thread which you want to present to the reader. So that means that when you want to synthesize all the calculations you've done, you wish to extract some specific message. This is going to happen when you write your master thesis, or when you write a scientific report, or you are in a company and you have to present the summary of some research which you did, because there's always some story you want to tell. So that means that we don't want you to, in the report, to answer question by question. We want you to write a story. And I'm going to show you or discuss today a little bit on how you actually make this story. However, the projects, as you see them, they will always be written in a kind of pedagogical way, where you build up your codes and all the formalism you need step by step. But then, when you run the calculations and you have the final stuff, then you lean back and you tell the reader, what is the message? So a typical message here could be that when you move on to real data, perhaps lasso regression or ridge regression are the favored methods. And ordinary least squares fails miserably, just to give you an example. So these are the kind of conclusions which you have to draw when you write a report. The format. So this is something which people have asked about during the lectures and the lab. So the format for the report is of the type of a PDF file. It can be a Word document. I mean, you decide what kind of format you want to present your results in. Then we want to see your programs. That means that when you give us the report, we also want to be able to run your program. Now, you can write your report as a Jupyter notebook, but be aware that when you run it when you present it as a Jupyter notebook, the Jupyter notebook will contain all the runs you did. So one thing you could do then is actually to have the program you run as an appendix, and then write a standard scientific report before the appendix. So we can jump into the appendix and run the code. Or you have a PDF file or Word document or whatever, and then you have an additional folder or file with a Jupyter notebook, all the programs you have developed. And then ideally, we would like you to have some kind of folder with some test runs so that we can actually reproduce what your program is doing. And that has to do with reproducibility of science. You will be surprised to see how much science cannot be reproduced. There are too many scientific works where you have to simply trust the authors that what they have done is correct. And there's no way you can reproduce it in many cases. There's not enough detail. So we've had many cases where master students or PhD students have written to authors and asked them, I mean, how did you obtain these results? And there is no answer. And then at the end, you start doubting yourself whether you're able to reproduce what other people have done. So it's a part of, this is the kind of simpler part of scientific ethics in just making your science reproducible. So having some test outputs which we can run and say, okay, running the code, we get what you have in the folder. So it means that when you write the report and prepare everything, if you don't want to use Git or GitHub, you can always post on Canvas a zip file which contains the report, the codes, and eventual test runs. Or if you want to have everything on GitLab, GitHub, you can just send us the GitHub or GitLab link, make it accessible for us, and that repository should have the report. It should have the codes, obviously, because we want to see that what you have done is really something you have done. So if you hand in a report without a code which we can check, then we will obviously, first, we will ask you, please upload the report. And if nothing is uploaded, then we will start with the subtraction scheme on the number of scores, on the number of points you can score. Because without any code, we cannot be sure that people have actually done what they claim they have done. So you can use a Jupyter notebook to write the report, but keep in mind then that it becomes pretty messy. So let's take a look here, and these are things which we will keep discussing at the lab. So in the beginning, in the first project, we will always be a little bit lenient in the sense that we will not be perhaps too picky on the way the report ends up looking like. We don't look at grammar. I mean, you won't get score or deducted points if your language is not optimal. But clearly that's something which for your master thesis, on the other hand, that plays an important role. But if you now look at the website of the course, there is a link here. You go to the doc, this is at the GitHub address, and you go to projects. And if you go to projects, then you will find the way we create, and there's also a report example here. But if you look at the evaluation form here, this tells you on how we actually give you a score. So we want you to have an abstract, which is the main summary, where you simply state what you found. If you have some numerical results, you can state them as well. We got this in these numbers. Compared with the previous literature, our result is much, much better than what was done earlier, and so on. You normally don't criticize other people in scientific articles. We try to keep a very low-key style. Then you should have an introduction, and if you look down here a little bit, you will find a little bit more about the basic structure on how to write a good scientific report. So the typical introduction, so I'm just going to go through some of these steps, but I invite you to take a look at them. So some of you have written scientific reports before, but many of you come from departments where there is no tradition in writing a report in the bachelor degree. So this serves also as a kind of training for those of you who, when you come to the point where you have to write a master thesis or you're writing your first scientific article, because the basic structure is essentially the same. So the introduction has typically 3 parts. One, where you put things into context and you try to explain why this is interesting to the reader. Then there is a part where you explain what you have developed. And then the final part would just be statements like, in section this and this, you will find these results. And in section that, you will find the conclusions and so on. So this is a typical structure of an introduction. And the motivation and you putting things into context is very important. Many people, and you will notice that later on as well, many people, when they read something, they read the introduction and they read the conclusion. So pay attention to what you put in the introduction and conclusion. If they are well written, people will often say, okay, this was interesting, maybe I should read more. Then the next part is like the theory part, where you discuss the methods. And you can split this in two parts actually, because we will also give you scores on the implementation, whether the code is readable or not. There's typically a theory part. So if you look at the first exercise part A, that could be something which enters the theory part. Similarly, there's a question later on this bias-variance trade-off, where you have to make some derivations. That's also something you can put in the theory part, or you could have it in the appendix. So the appendix is a place where you would typically add additional material. And the results always give a critical discussion, relate your work to other calculation studies if you can. So one of the things which is nice with many of the data sets which are included in scikit-learn, for instance, they do actually, these are data sets which have been researched a lot. So you will find links to scientific articles which have studied this data set. So when you implement your neural network or logistic regression or whatever, you can always compare that to what has been done before. And that's something which is part of the scientific dialogue, that you present your result and you have to relate it, if you can do, to what has been done. Now, one thing which makes it make the Jupyter Notebook a little bit, I would say, less straightforward in presenting the results like this, is that when you run the Jupyter Notebook, you generate tons of figures, right? And that means that the readability can easily be less, the report can be less readable because there are too many figures, right? So you have to think of the way if you want to use a Jupyter Notebook, I would recommend to produce the figures for the report itself and save them and then place them as a figure in the Jupyter Notebook and have the code at the end of the Jupyter Notebook. That makes it much more readable. So remember that having good figures and good tables can often really improve the readability and you conveying the message properly. You probably heard this kind of statement that a figure says more than 1,000 words. So if it's properly made and it has a good caption, and remember to put labels. I mean, if the things are not well presented, we do also subtraction of points. We don't want you to write messy reports. So figures should have labels, they should have on the axis and tell what they are, and they should have a caption. So if you write a good report, the reader can actually get most of the main results by just looking at the figures and tables and reading the figure captions. Any questions so far? Okay, so for some of you, this is a little bit boring, but many of you have never written a report before. So, and then you would have conclusions and some perspectives for future work. And we also want you to have references, and you can place additional stuff in appendices. Many people nowadays, they actually have additional or supplementary material on their GitHub sites, on their website. That's fully possible. Many of you, when you're going to write your master thesis, you will have many additional calculations which you can place on the website. And that means that a potential reader can then go to these links and download or just watch additional results. So many people, if you're doing fluid mechanics, you will often have animations, and these are things which are not easy to include in a normal report, and then you could typically have a link to an animation. So if you want to have animations in your reports, you can always post them as on your GitHub site or on other sites as a link in the report. And then we invite you to take a look at the way we actually set up the scores. So you can see the type of points which we give for the different parts. So code implementation, formalism, the introduction. So we give you scores according to the different parts of the report. And there is referencing is important. So you should always have at least one reference. So if you want to have a reference to some of the textbooks, you should do that. A reference to, let's say, bias variance, trade-off, and so on. Try to avoid Wikipedia as a reference, because when you write your master thesis, not everybody will accept Wikipedia as a reference. Scientific journals do not accept it, because Wikipedia, even though it's pretty good, I mean, there are still articles which haven't been properly peer-reviewed. It doesn't mean that they're wrong. I use Wikipedia continuously, but it's less used in scientific citations. And then clearly you can see the table. This will give you the final grade when you add up everything. Questions so far about the reports? Now don't hesitate, yeah?
Who should we have back in mind when we write it? So what level should we explain things?
So that's a very good question. And to those of you online, the question is about what kind of level should we place the report? So I'd say if you look at the lecture slides here, and you should think of somebody who is at the end of the bachelor degree, beginning of a master degree. That would be the typical level. And there are derivations, like you don't need to go through all derivations. You can actually, if you look at ordinary least squares, you can just state the equation. These are the equations for ordinary least squares, and then you give a reference. So some of these things are things which you've gone through in the lectures, and you don't need to do a derivation of all the equations you've done. You can just simply state these are the equations, add some text, and then the most important thing is actually how you have implemented it. That's the thing we are actually looking after. So you don't need to do a very in-depth theory derivations, but you should describe the methods, their pros and cons. There are many different ways of writing the reports. We put in, there's an example which you can find in here. So there's a report example, you can take a look at it. I'm going to put in some more examples here. And this is a report which was written, I think this was for project number 2. So this is just, you don't need like things like this, but this would be a typical example. It was applied to a system this was more physics oriented. And you can see now a typical abstract, a typical introduction here, where you motivate the reader. Typical introductions are 1 page, perhaps 2 pages, a description of the method. And then when you just do it here, you have to load more pages. A description of linear regression. You can have excerpts of codes and things like that. And then there's a discussion of the bias variance trade-off. So these are typical examples on how you would actually write the report. So I'm going to put in more examples so you have more you can look at. But the lab, either whether you participate in a digital lab or the in-person lab, I mean, is also the place where you just can ask questions and never hesitate to use these opportunities to ask questions. Okay. So I also wanted to bring up another technicality, and I'm going to do that with slides before we move back to the analysis of ridge and lasso regression. And this has to do with the intercept and the comparison with scikit-learn and your own code. So I just want to, in the slides here for this week, you will find an additional material on the role of the intercept. And so let me just go through this using the slides. And I hope you don't, I don't want to abuse too much with slides. So after we've done this, we're going to go back to the whiteboard. But this is actually something which is useful to have studied a little bit more in detail. And it applies mostly to you performing a polynomial fit. This is actually where this problem pops up. In many other cases, you may not do a polynomial fit, and then this is not a problem, okay? And it has to do with scaling. So let me just bring up the slides here. And so if you scroll down a little bit on today's material and tomorrow's material, we're just going to go down a little bit here. And I wanted to just go down, and then we are going to go up again. So I just put it down a little bit, but I thought of bringing up this technicality before we dive into the details of the singular value decomposition. So the thing is, and this is something you noted last week and the week before, is that scikit-learn, when you're comparing your code for, let's say, the inversion of the design matrix with scikit-learn, you have to be a little bit careful, because scikit-learn does a subtraction of the mean value automatically without warning you. And there is a flag, which many of you discussed at the lab, which is called intercept equal to false, which actually means the opposite. It means that the intercept is included. So if you do intercept with true, it takes away normally the intercept, but then it reconstructs the intercept for you. Yeah?
Do we have to use scikit-learn?
No.
We can use, for example, chaos.
Yeah. So again, we want to give you maximum flexibility here. So some people want to write their own codes. Feel free to do that. We had people writing in C++, Fortran, Julia, or Python, writing everything from scratch. If you wish to use scikit-learn, that has lots of features like reading in files. You can use pandas. You can use the the train test split functionality, and so on. These are functions which make it a little bit easier to get started. You can obviously write these yourself. You can use PyTorch if you want to. So when you are a little bit in doubt whether your program is running correctly or not, you have, in a way, functionality in these libraries which allows you to compare your program with what these libraries have. And so in a certain sense, you can think of these libraries as a way to support you in assessing and checking that your program is running correctly. But when you do that, then you have to be a little bit careful, okay? And this is the kind of main message here in these notes, is that scikit-learn does things for you which needs some thinking sometime. And scikit-learn actually has also these ways of scaling your data. So one standard feature is actually that you subtract the mean value from every column in your design matrix. One of the reasons for that is to avoid that specific outliers get emphasized in your fit. Also, if you include the intercept can be a large number, whereas many of the other parameters which you end up fitting can be pretty small. So sometimes you want to scale the data so that you have data which are pretty uniform for all the features which you have. Sometimes you have data in kilometers, some give you data in meters, and so on. If you look at project number 1, there is a question whether you need to scale or not. If you look at your X values, they are already scaled between 0 and 1 because you're asked to produce numbers between 0 and 1. So using this scaling feature in scikit-learn, for instance, where you scale your data to 0 and 1, there is no need of doing that, right? So you have to look at the data you generate, and you have to decide whether you need to scale or not. So if you look at the function values you will produce, they will often be in a limited range, so perhaps there's no need to scale them. If you produce numbers from, let's say, 1 billion to plus 100 billions, then you may think of scaling your data. So the first example you have is actually a vanilla case, as we normally call them, because the data are between 0 and 1, the X and Y values which you generate. So when you do things, scikit-learn has this possibility to actually do this automatically for you. But when you want to compare, what you would often do then is to subtract from in your design matrix, you would actually subtract the mean value. So let's try to take a look at what this centering means mathematically, so that you see what is going on. So as I said, scikit-learn would often just take out the intercept column, which is just once. Because if you regularize this by subtracting the mean, then you would just have zeros. And then if you want to invert the matrix, you run into problems. So if you take a look here and look at the loss function or cost function which we have in linear regression, what I did here was actually to single out the term which is related to the intercept. And then you have the remaining terms. So by taking away the intercept, you're actually having a optimization problem which uses all the optimization power on the other parameters. So what we have done is to single out the beta zero term. And if you now want to optimize a problem, you calculate these different derivatives. So if you take the derivative with respect to beta zero, you're just having this specific term here. That's a derivative with respect to beta zero, the intercept. So keep in mind, as I said, that this is a problem which is pertinent to the polynomial fitting, where you actually want to have the intercept. Many of the problems you're not fitting a polynomial. Then you can rewrite this expression here by multiplying away the 2 over n term, and you want this to be 0, obviously. And that means that you can define the intercept in terms of the sum over the y values times the parameters you fitted. So if you have these parameters, this is something you have, this is defined by your design matrix, you can actually recover the intercept. So this is just a constant. So this is, when you sum it up here, it just gives you n times beta 0, right? So beta 0 is a constant. And then you see now if you sum it up, suppose now you have only 2 parameters. This is just to simplify things. So you have a beta 0 and beta 1. I sum up, this is just a constant, so that gives me n times beta 0. I have a sum over the y values. And then clearly if I divide with 1 over n, this is just the sample mean of the yi's you have. And this is something you can calculate because you have the yi's. And then in the fitting problem, you're getting these parameters beta 1 here. So this is a constant, I'm just putting it out here. So if we then define this quantity mu1, which is the sum over these terms here, there should not be a parenthesis here. Then you can also define the value of the outputs. Then when you've done the fit, you can actually reconstruct the intercept by taking this parameter here, which is the average of the output sample, the sample outputs, multiplied with the parameters you did fit, and multiplied with these elements in the design matrix. So in a general case, where you have more parameters, you would simply have to recalculate this quantity here. So this is a little bit about the mathematics and how you can reconstruct the intercept without having made a fit of the intercept. So scikit-learn actually by default does not include beta 0. So if you want to take an example here, there's actually an example code in here. So what you need now, when you look at your design matrix, you can actually scale your design matrix column by column by subtracting the mean value for that quantity. So that's the one thing you would do. And then you would look at the mean value for you. So the y tilde, which you would have here, would be a scaled output where you've subtracted the mean value for the output. So let's look at an example here. And this is an example which one of the TAs made 2 or 3 years ago. And this specific case is an example where we now are making a polynomial fit where the intercept is 2, the slope is 0.5, and then the second order term is 3.7. And what we do now is we simply set up a data set and we produce a function which now is a second order polynomial. And then we include the intercept in the design matrix, which is here. We have a parameter fit beta, so we perform the fit, we invert the matrix. This is also something which we will discuss today. When you're inverting the matrices, just a small hint, use the pseudo-inverse. The pseudo-inverse uses the singular value decomposition to calculate the inverse of a matrix in case you're getting close to, let's say, a determinant which is close to 0. So don't use the inv function in NumPy, but use the pseudo-inverse function. We're going to discuss that a little bit more today. So when you're setting up your own function, use always the pseudo-inverse, unless you're dealing with ridge regression where you have a parameter lambda, which really helps you in avoiding the eventual determinant which is equal to 0. So in this specific case, when you now want to compare with scikit-learn, you have to put in fit intercept equal false. So I actually spent some hours because I put true, and I thought that being true means that you included the intercept. That's actually the opposite. And then I'm doing the predictions and comparing. Now, the next thing is I'm producing a design matrix which does not include the intercept. So in project 1, feel free to include the intercept. Don't complicate things, but then just keep in mind that if you want to compare with scikit-learn, just to be sure that everything is running correctly, then you need to have false on the intercept. Just keep that in mind if you want to make the comparison. But I would say for project number 1, just keep the intercept. Then in this specific case, I'm now setting up a matrix which does not contain the intercept, and then I put fit intercept equal true. You don't need to do that. I calculate the average for the output, and I calculate the average for the design matrix. And when I make the fit now, I have my design matrix minus the average, and I have my fit with y minus its average. And then the intercept is something which I then can reconstruct with those formulas which I showed you in the slides here before we started to look at the program. So I invite you to take a look at the equations. It's not that difficult. And then what we do then is that we simply perform a fit here. And you can see now that the true beta values are this. This is my fitted beta. And this is what scikit-learn does when I have the intercept. And then I have now the mean squared error with intercept column is now the same as the one with the us taking away the intercept. So when I do ordinary least squares, there is not a difference. But when I start with ridge regression, I can actually get a much better mean squared error. And that's due to this dependence of this parameter lambda, which we're coming back to. So what you would typically see then is that you have an sklearn fit with intercept false. So at the end here in the code, we're actually adding back when we're making the plot. So this is the model. And then we calculate the intercept by the formula which you saw. So we add them back again. And this is what we plot. So it means that all the calculations should actually give the same result when we add back the intercept. So the intercept is the value or output target variable when all our features are 0 and our function crosses the y-axis. And you see now that when you print it, that both methods give the same mean squared error, they should. However, when we move to, for example, ridge regression, the way you treat the intercept may actually give a larger or smaller mean squared error. And that has to do with the fact that we add a term like this one when we do ridge regression. And similarly for lasso regression, we add a similar term like this one. So taking away the intercept here means that you're going to have a different optimization problem. So the parameter lambda, which you see in lasso regression and ridge regression, this parameter here puts actually a specific emphasis. If this parameter is large and you keep the intercept, that will actually play a role when you make the fit. And that can actually increase your mean squared error. And in the examples which you see here, you will actually see that in more detail. So in the code examples which you have here, there is an example where we do everything. So we have a polynomial of degree 20, and we have specific values of lambda, and this is what you actually will end up doing in project 1 as well. You will run through a set of values lambda. Later today, we are going to also see why this lambda should not be 0, or if it's 0, you're getting ordinary least squares. And if it's negative, you're going to get results which don't make sense. So lambda is a parameter which is always larger than 0. But we are coming back to why that's important. So in this specific case, we are making a fit, and in ridge regression here, we actually put an intercept equal to false. And when we run the code then, what you will see is that we are going hopefully to get exactly the same result. So you will see now the beta values for the ridge implementation, and then you see those for scikit-learn. It's essentially the same result to numerical precision. And you will also see that the mean squared errors are the same. And then this is for my own implementation, and this is for what scikit-learn gives. And then when you increase the parameter lambda, you will then see that the mean squared error can actually increase, as you see here. And we are coming back to why this increases as a function of this parameter lambda. But if you look at the plot, this is one of the things which is a little bit assuring, is that we get the same results, whether we use scikit-learn or standard ridge regression with our own code. Then you can actually take away the mean. So in this specific case, I'm constructing a design matrix, as you see in this statement here, without the intercept column. And then I have to be a little bit careful to rewrite my scaled design matrix by subtracting the mean value, as you see here. And I do the same with the data I want to use in the training, the output I want to use in the training, which now has this mean value subtracted. And then I perform the fit. So I have 6 lambda values, which go on a log scale from 10 to the minus 4 to 10 to the 2. And what we need to discuss a little bit more in detail now is what actually happens mathematically when we plug in this regularization parameter or hyperparameter lambda. But what's special in this case is actually then when we look at the calculations here and we look at the plot at the end, is that in general, due to the fact that we don't fit the intercept, is that the mean squared error is actually smaller when we take away the intercept with ridge regression than we had when we included the intercept. So this is something to keep in mind when you're performing a scaling of your models. And when you use ridge and lasso regression, you're actually putting some penalization on the intercept multiplied by this parameter lambda. So just to remind you quickly, when you move away from ordinary least squares, what happens is that you have an optimization problem where you now include this parameter lambda here. And that will obviously put some more weight on the intercept itself. And that can lead to a mean squared error, which can be larger or smaller compared to the one when you included the intercept. So scaling data, in particular when you do a polynomial fit, be a little bit careful when you compare your own code. If you're interested in comparing with scikit-learn, I mean, there's probably no problem. You can fit with the intercept or without the intercept. So this is something you just have to be aware of. And the way you scale the data depends also a lot on the type of data you have. So like in the first example, there is actually almost no need to scale your data. Any questions about technicality? So I'm using some of these lectures also to discuss the projects, because as I said, this is a project-based course, right? So I hope you don't mind that I also discuss some technicalities around the projects. Any questions about the project itself? Something which is unclear or something missing? Yeah? Hey, could you say it a little bit louder?
Well, it's relevant for the project and the exercises that we have done. I noticed that the mean square error, it gets scaled when you scale the data. Why is that?
So the mean square error does not get scaled?
No, when I scaled the data,
yeah.
I saw that the mean square error also got scaled compared to when the data was not scaled. Like it increased by a factor of 4 in my example when I scaled the data.
Okay. So to those of you online, this is a question about the mean square error and what happens when you scale the data. And what you saw is that the mean square error actually increased when you upscale the data. I don't have a clear answer to that one, so I would like to look at it. So I don't have an immediate reasonable or meaningful answer. I need to look at your case. More questions about the project itself or things related to the project, things which are unclear or whatever. Okay, so what I wanted to do now is to go back to the whiteboard, and we are going to look at more the mathematics of ridge regression and lasso regression. And we need an intermediate step, and this is about the singular value decomposition. We discussed that last week. And by the way, before we move on with project number, with the, oops, let me just bring this up again. So just one more hint for project number 1. So if you go back to the slides from last week, there is actually an example on how to get started with coding this Franke function and how to create a 2-dimensional data set. So if you're a little bit in doubt on how to set up X and Y, take a look at that example from week 35. So my advice in general, I mean the code examples which you see in the slides, they are meant as a help to you, to get you started. So some of these things are just plain technicalities, and seeing such an example can help in setting up the data set. Also, if you're a little bit in doubt whether you want to jump into the 2-dimensional case immediately, you can develop all your machinery for a 1-dimensional case. And then at the end, you just replace the 1-dimensional function with the actual function which we have here. So this function serves also as a kind of stepping stone towards the topographic data, which we have at the end. Because then you've gotten used to deal with a function which has an X and Y dependence. Because what you're going to look at as real data is actually the elevation as a function of the position. That means elevation as a function of X and Y. So feel free to use whatever you see in these lecture notes. And this is just to help you in getting started. So you won't get penalized if you use what's in the lecture notes, period. This is meant as a help, as a guide. Some of you feel more familiar and you want to write your own code from scratch, please feel free to do that. If you want to use this material, use it as much as you want. Okay, I spent a little bit of time on discussing the project. I think that is important. And we are going to take a small break now. And after the break, we are going to discuss the singular value decomposition and the lasso and ridge. So for the rest of this week, we are going to look at the mathematics both from a more mathematical linear algebra point of view, but we're also going to look at the statistical interpretation of lasso regression and ridge regression. And for the latter, we will need what we started to look at last week, which is called Bayes' theorem. And we are going to see that ridge regression can be interpreted as a parameter beta, which is given by a normal distribution, whereas lasso regression can then be interpreted as a parameter beta being generated by a Laplace distribution. And we're going to see these connections. But first, we need to look at the singular value decomposition. And we started to scratch the surface last week. So today, we're just going to dive more into the mathematics here. So the theorem itself, if you have a matrix which is near singular or singular, you can actually decompose in terms of the singular value decomposition the matrix anyway. So if you're thinking of a square matrix which can have a determinant which is zero, some eigenvalues which are zero, that means that you cannot decompose the matrix. However, the singular value decomposition theorem says that you can actually decompose this matrix in terms of one matrix which is an orthogonal or unitary matrix, another matrix which has the same properties but of another dimensionality, and then a matrix which then contains the so-called singular values, which you can, in a way, interpret as the eigenvalues. So the theorem itself is perhaps one of the most powerful ones in linear algebra. And what we discussed last time was some examples of matrices. So like this matrix X, which you see here, which has a determinant which is zero. And the matrix is singular and its inverse is then undefined. And that's equivalent to saying that the matrix has at least an eigenvalue which is zero, and which you can easily prove from this matrix here. This is a matrix, however, which you can decompose according to the singular value decomposition theorem, and we are going to look into that one. So the basic math of the theorem here is that you can decompose a matrix. So in this specific case, the matrix is a square matrix, but it doesn't need to be a square matrix. So a square matrix, it can be a so-called normal matrix, which can be diagonalized, or it does not need to be a normal matrix. It could be a defective matrix like the one you see here. And the theorem simply states that you can actually split a matrix X, or you can rewrite it in terms of two orthogonal / unitary matrices. We are going to assume basically that all the parameters which we deal with are real parameters. So we are essentially going to deal with orthogonal matrices. And then a matrix which contains the singular values. And we are going now to look at examples here. So if you look at a matrix like the one which you saw here, this 1 minus 1, 1 minus 1, which is a defective matrix, then this matrix can be decomposed into three matrices. One, where you have a so-called singular value, which is equal to 2, and then values which are 0. So that reflects the fact that this is a matrix which has a 0 eigenvalue. And this is the matrix U, and this is the matrix V. And what we are going to do now is actually use this to understand a little bit better what is going on with the lasso, ridge, and ordinary least squares. Okay, so it seems that I forgot to share here for those of you online. I'm sorry for that. So I was actually looking at my slides. So let me just bring up the slides here for those online. I apologize for that. So these matrices, this sigma has elements which can be 0, and it has elements along the diagonal which are non-zero, and they are ordered as a descending series. So the first eigenvalue is the largest one, and these are positive values. All the singular values are positive. So they're larger than 0, and then you have a set of values which are equal to 0. So let's now go down a little bit and switch to the whiteboard and look at how we can connect this theorem to the ridge regression, ordinary least squares, and how we can reanalyze results in terms of these quantities. So what we have assumed now is that we have, in ordinary least squares, we have typically a design matrix. So OLS stands for ordinary least squares. So we have a design matrix which is used to find the optimal values for the parameters beta, where we have a matrix we want to invert, -1 of x transpose times y. If we look at ridge regression, and let's now just focus on ridge and ordinary least squares. In that case, the parameters beta, and we're going to put a subscript OLS and a subscript ridge here, are given by a matrix x of t of x plus a matrix, a diagonal matrix, inverse, multiplied with x of t and of gamma. And this parameter lambda, as we will see later, is always larger than 0. When it's equal to 0, we just have ordinary least squares. And to remind you of the dimensionalities here, so we have assumed now that X is not necessarily a square matrix. So it's we assume that it has real elements, and it's a matrix of dimensionality n times p, where p is typically the number of features. In our case, in project 1, this is going to be the number of parameters in a polynomial fit. And then we have that xt times x is then a matrix of dimensionality p times p. Just a quick reminder of the dimensionalities here. The parameter beta is given by p elements. So what we can do now, and the power of this SVD, is that allows us also to calculate a pseudo-inverse. So as a kind of safety measure, in case you have problems with the determinants which can be near 0, I always recommend to use the pseudo-inverse, and that follows from Python in the NumPy linear algebra package. The matrix I, which you see here, the matrix I which we put in here, is a matrix which has a dimensionality p times p. So when I now perform the SVD decomposition of the design matrix X, I can rewrite that one as a matrix U, and then I have the singular values multiplied with the matrix T. And in our case now, U is a matrix which is an orthogonal matrix, which means that if I have U transpose times U, this is equal to the identity matrix. So ones along the diagonal, which means that the transpose is the inverse of the matrix. So this is something we are going to use when we're going to look at how to interpret the ridge and ordinary least squares. And then we have the matrix V is also an orthogonal matrix. Alternatively, can be unitary. I hope you can see the difference between my V's and U's here. So U has a dimensionality of n times n, and V has a dimensionality now of p times p, and this singular matrix, the singular value matrix, is going to have values which goes like sigma 1, or we start with 0 here, up to sigma p minus 1, and then the rest are going to be zeros. And this is a matrix which has dimensionality n times p. So this singular value decomposition, even if the matrix can be defective, it always exists. It exists always. You can always perform a singular value decomposition of a matrix. Okay, so that's a very important aspect. Now, it means that if you look at the matrix U, we can write this out in terms of the vectors. So I'm trying to write this, this is an uppercase letter. This is the vector U. This is the column vectors, U1. So it's an attempt to make them bold-faced. And these are orthogonal vectors. which means that if I take the norm of these vectors, if I try to calculate a u of I with u of j, so this is a norm, a way to indicate the norm of a vector. This is the same as a u of I transpose of u of j. This is equal to delta ij. So every column here is a so-called vector for the matrix U, and these vectors are all orthogonal to each other, and they are normalized to 1. So they are normally called orthonormal vectors. The same happens with the matrix V. That has its own vectors, V0, V1. So every element here has now n, for the matrix U, everyone has n elements. And similarly for the vectors V, they have p elements, because V is a p times p matrix, up to p minus 1. And again, V of I transpose times V of j is actually delta ij here. Now, an example of such a matrix which you have, I just wanted to bring up a matrix sigma. So for this matrix sigma, what we have is that these singular values, they are normally sorted as a kind of descending series, in the sense that the first singular value is larger than the next one, and so on, up to sigma p minus 1, and this is larger than 0. And then you have a set of zeros. Now, in the analysis which we are going to make, we are assuming that n is larger or equal than p. In general, what happens is that we have often many more entries than features. So remember now that p, I'm using a kind of labeling in my design matrix, so that the columns refer to the features, and we have p features, and the rows refers to the entries, the data points which we have. So this is my way of ordering and setting up a matrix. In many other textbooks, you will find the opposite. So you will have the rows being the features and the columns being the data entries. So just keep that in mind when you're setting up your problems, because the matrices which we're dealing with will not be square matrices in general, because we typically have many more data entries than we have features. So if you have 30,000 credit card clients, and you want to figure out whether they will default or not on their credit card debt, you will typically have something like 30 entries about each credit card holder, which could be age, sex, education level, employment, non-employment, etc., etc. And typically these features are normally, in most of the cases we are going to study, it's represented by number which is much smaller than the data entries. So we are going to typically be in a situation where the number of entries is in general much larger than the number of features. Okay, so let's take a look at one of these matrices here. So as an example, we could now take a singular value matrix which looks like this, 2, 0, 0, 1, 0, 0. And it's pretty common to rewrite this in the literature like a sigma tilde 0, like this. So this is a 3x2 matrix. And you can rewrite that one in terms of a matrix which is 2x2 and a matrix which has just one row in this specific case. Keep in mind also that when I calculate sigma t, this is a matrix which will have dimensionality p times p. So if I take this specific matrix, for this example, if I calculate, no, sorry, this was wrong actually. I was looking at the wrong line here. So if I calculate that matrix here, so if I take the transpose, and I calculate, so the transpose would just be 2, 0, 0, and then I have 0, 1, 0, and this is multiplied with 2, 0, 0, 1, 0, 0. This is a 2x3 matrix, This is a 3×2 matrix, and this gives us a matrix which is equal to 4, 0, 0, and 1 when you do the algebra here. Now, this is just an example. Then you have another matrix. If you take sigma times sigma t, the transpose one, this becomes a matrix of dimensionality n times n. Now let's go back to the ordinary least squares. And let's make a link with the singular value decomposition and ordinary least squares. So we have, and what we are going to do now is that we are going to make a singular value decomposition on ordinary least squares in order to try to figure out the mathematical link with SVD and the ordinary least squares. There are many interesting links actually, and I hope I can make you follow the kind of main line here. So if I do a singular value decomposition of that one, this is a matrix which can cause problems. This could be a defective matrix. It could be a matrix with a determinant equal to 0. So if I now look at it, what I have is I get sigma t times u of t, and then I have u times sigma times v of t. So I'm just plugging in the singular value decomposition of the matrix. Now, this matrix here, this matrix product is actually the identity matrix. So that means that this becomes V of sigma t times sigma times V of t. And we could rewrite it in terms of this matrix, which I wrote up here, this matrix sigma tilde, but let's just keep it like it is. Then, if I now go back to my expression, so what I have is my model, y tilde, is given by x of beta, and now I'm putting a hat on beta because this is my optimal beta. So let's see what the vectors y look like compared to the original vector y. So we have an output y, and then I have a y tilde, which is our model. So how do these relate to each other? Can we make a mathematical statement which relates the two? Now, this is something we can now rewrite as x, and then I'm just plugging in the expression from ordinary least squares, minus, and then I have xt times y here. So I just plugged in the expression for beta, the optimal ones after the optimization. If I then put in things here, what I have is that this becomes equal to u times sigma of v of t. So this is this term here, which I'm plugging in. Then I have the matrix I want to invert. So this is v of sigma t of sigma of t, sigma of v of t inverse. And this is multiplied with v sigma transpose times u transpose times y. So you may ask now, well, hey, what is this guy doing? I mean, it's just overcomplicating things, right? What's the point? The point is that we can actually relate the two vectors y and y tilde by the vectors of an orthogonal transformation. And that gives a mathematical interpretation when we in particular come to ridge regression, where we can make a simple comparison and see what happens when we do ridge regression compared with ordinary least squares. Okay, so what we need now is a little help. And if you have two matrices, A and B, and these are square matrices, and they are invertible. Then what I have is that if I have the product of matrix AB minus 1, this is equal to B minus 1, inverse times that one. I don't know if you've seen this relation. It's actually not so difficult to prove. Now, we started with a matrix X transpose times X, which may not be invertible, right? So we could actually run into deep problems and have a matrix which cannot be inverted. And that's why we are here now, looking at the singular value decomposition. Now, if you look at what we did with the singular value decomposition, and you look at the matrices which we have to invert, if you look at these guys here, and you think of, you could now think of this as being a matrix A, this as being a matrix A, and this is a matrix C, so we would actually have more matrices. Are these invertible matrices? Or not? So if I want to use this nice feature which you see here, I actually have to have that the matrices which I want to invert, this V times sigma transpose times sigma times V transpose, they actually can be inverted. So just let me give you some hints here now, right? And if you go back to the definitions, so if you look at this example, which we did with the sigma t times sigma, this is a matrix which now contains only the singular values, and they are larger than 0. So if you look at this matrix here, what is your feeling? Can I invert that one? Yeah, everybody agrees with that. Now let's go back to the definition. This is the power of the singular value decomposition. If you go back to here, what does this say actually to us about invertibility? Yeah? Yes. So we have actually rewritten something which was ugly and bad, which was not necessarily invertible, into something which is invertible. Isn't that nice? So that means that when you go back here, you should also keep in mind when you look at this denominator which we have, and one of the things we need to keep in mind then is that if we look at this matrix V, V of times V of t is equal to Vt of V, and that's the identity matrix. That is a matrix which simply then means that V is equal to V transpose inverse. So I can actually put that one back in here, and in here, and then I can use the orthogonality of these matrices to get rid of this term and that term. Because what I'm going to get then is simply the following. So if I use this, so let's just put this in parentheses here. Actually, these statements are some of these kind of what I call the hidden gems in linear algebra. I am a linear algebra aficionado. I mean, this is really something. When I saw linear algebra the first time, I really fell in love with it. And there are so many hidden gems which we forget about. So I'm trying to bring up some of them here. Okay, so if we now rewrite this, so what we have then, and let me just look back at my cheat sheet here, so I do things correctly. So what I get then is that this model which we have, y tilde, is now equal to u of sigma of Vt, and then it's multiplied with V, and then I have a denominator which is sigma t, sigma minus 1, and then I have V transpose times V times sigma of t times u of t times y. And then I can use the orthogonality relation, so this gives me the unit matrix, this gives me the same, and then I have in the denominator, I have a sigma times sigma t transpose, so these cancel each other. So what I end up with then is actually u times u of t times y, and then I can write it out in terms of the vectors of the matrix. So this is actually given by a sum of the vectors which we have, the column vectors of the matrix, of u of I transpose, and this is multiplied with the vector y. So what it says is that the vectors U, the column vectors of the orthogonal matrix, they give us the relation between the original data set. So this is a kind of projection of the original data set into the model which we've made. So this gives a precise mathematical link between the model which we've made and the data which we have. Now, where does this lead us? Why is this interesting? So we can redo the same exercise with the expressions for ridge regression. So if I look at ridge regression, so let's bring that up again. What we have then is a beta, and now I'm just going to skip the subscript, which goes like x of t times x plus lambda is a parameter times this identity matrix minus 1 inverse x of t times y. Then I can now repeat the same exercise, which I did here. And if I do the same exercise, what I have now is a relation between y and the model and the data which I have. And we are going to get then u times sigma times v of t. And now I'm just rewriting the matrix here in terms of v. And then I have the sigma t times sigma times v of t plus lambda of I. And you see now I can rewrite this one in terms of v times v of t minus 1. And this is multiplied with the matrix U of sigma times v of t transpose multiplied with y. So if I now put in this v of vt in here, I can repeat the same trick I did with the denominator, and then you will see that I will get a term v of t multiplied with the v again, and then I will have a similar term here with the v multiplied with v transpose, and that due to the orthogonality, we get rid of that term. So that means that when I do everything here, what I get is that the expression I have is, when I do the math here, what I get now is that this is given by a sum over all the vectors which we have of n minus 1 of u of j of t, but now it's multiplied with the singular values squared, and I have a sigma j squared plus lambda and multiplied with y. So we put a ridge here, so this is a ridge. And then we are going to put a y OLS, which is given by just uj of t, sum of j equals 0 up to n minus 1, and multiplied with a vector y. So these are different projections of the original data set. Now look at this expression now, and I want to ask you one thing. So remember now that this, we have assumed now that n is larger than p, and these singular values, sigma 0 larger than sigma 1, etc., and larger than sigma p minus 1, and these are larger than 0. And then for sigma p, etc., up to sigma p minus 1, no, sigma n minus 1, they are equal to 0. Now, if you look at the two sums you have, the one for ridge and the one for ordinary least squares, and you focus on the summations here, what do you see as a change here? So look at the values of the singular values and look at the summations. Yeah? Yes. So since sigma j is 0, when we go beyond dimensionality or P, then all the other terms are zero. So that means that what happens now is that in this specific case, we project out only some specific orthogonal vectors. So what we have now is that ridge gives us now a sigma of j equals 0 up to p minus 1, because all the other ones are just 0, right? So if the singular values are 0 beyond a certain point, then the sum runs only up to these values here. Then I have a sigma j squared of sigma j squared plus lambda. Now, what happens if lambda is large? So let me just ask you. So remember now that lambda is a parameter when lambda is large. So take a closer look at the expression here, because this is about the fundamental properties of ridge regression. So if I make lambda large, lambda is a parameter I can choose. So now I can drive it to become a large parameter. Yeah?
I have a question about the sigma p to sigma n minus 1.
Yeah?
I was wondering where they're at in the matrix, because the matrix...
So the matrix actually doesn't include them. Yeah. So in a sense, when you do the matrix multiplication, it shouldn't, you could actually just put it to p minus 1 immediately. Yeah. So it means that you're, yeah, there's another. Yeah.
It's large. If it's large, the small eigenvalues will be less focused on, because they will be unproportioned by the...
Exactly. So this is a very important feature. This is a very important feature. Yeah, you see when you have this Siri on your laptop, it actually comes up, and it actually said the answer, that's what I figured. Okay, that's a danger of having this kind of things on. Okay, so what happens when you put lambda large and your eigenvalue is small? That means that some of the features which you have may be taken out or just reduced. So suppose now you have 100 features and then you make lambda large. That means that you can actually, by tuning lambda, you can get rid of features in your matrix here. So it's a way to think of feature reduction. And again, reducing your number of features is the same as a dimensionality reduction of the problem. So sometimes you're looking after the interesting features. So ridge, in a way, is a way to drive away specific features in your problem. Now, there's much more to the picture here, and actually the lovely thing comes when you want to link this with the covariance, which we discussed last week. Because what you see here is extremely interesting in terms of the covariance as well. And later we are going to discuss something which is called the principal component analysis, which is actually linked to the kind of analysis we're making here. What you're also going to see is that lasso regression, if you look at this equation here the properties do not vanish, because when lambda goes to infinity, you will have a slowly converging series, right? So the features will still be there, but their contribution will be marginal. Lasso regression, on the other hand, actually puts some features to exactly 0. And this is something we are going to see through examples. So an easy test of everything you're doing is actually to put in. So if we now look at so let's just take a look at a small example here. So if you, let me see where I did place it actually. Yeah, one thing we could do now, a simple example. This is obviously to make the matrix we want to invert into the diagonal matrix, or the unit matrix. If we do that, then what happens is that ordinary least squares won't change, but the ridge regression, so in that specific case, we will have that the y tilde ordinary least squares is going to be the same as before. And I'm just going to write it like this, u of mu t. These are the vectors now multiplied with y. If I, on the other hand, look at ridge, and I take this y ridge here, and I just plug in the unit matrix, what I'm going to get then is that this is simply going to be given by a matrix. So in this specific case, what we have to use is that beta optimal or ridge is simply equal to 1 over the identity matrix plus lambda times the identity matrix multiplied with minus 1 of xt times y. So that means that what I have now is simply 1 divided by the identity matrix plus lambda times the identity matrix. And this is given by beta OLS. And where beta OLS now is simply given by, just to remind you of that, this is a very simple case you can test. This is given by xt times x inverse xt times y. And we put xt, x transpose times x inverse equal to the identity matrix. So that simply tells us now that there is a scaling of the ridge result with respect to the ordinary least squares by a factor which goes like 1 plus lambda, and this lambda is now the parameter which you tune. And that simply tells you now that you can really tune down all the parameters. In the equation which you have up here, on the other hand, what you're doing now, since you have the singular values, is that you will trigger, in the last case, you are going to democratically reduce all the features, whereas here you can actually select features you want to drive to 0. Not exactly to 0, but close to 0. Any questions so far? So I hope I'm not bringing in too much mathematics, but I think it's important to actually see some of these connections, because it gives you the possibility to make an analysis of what these different methods actually mean. Now, but there's more to the picture than meets the eye here. There's something beautiful with the singular value decomposition, which allows you to rewrite the covariance matrix in terms of these orthogonal matrices. So let's look at that. That's another piece of information which is very useful. And then tomorrow we are going to try to bring many of these things together. So this is a small digression, and we are going back to the so-called covariance matrix. And you remember from last week that we actually defined the covariance of a specific matrix X. So we have our matrix X now. The design matrix contains elements x00, x01, up to x0p minus 1. And then we have xn minus 1, 0. And then we end up with xn minus 1 of p minus 1. So let me put this as an uppercase letter. You can rewrite this as a vector, a set of vectors. So we could have a vector x0, x1, and then to the x vector xp minus 1. That's another way to write the design matrix which we had. Now, what we defined last week was a covariance. So if you now think of the covariance, and let's take two of these vectors here. So let's take a vector. So these are now the vectors which you see on display here, the columns of that matrix, of the design matrix. And suppose now we wanted the covariance of two vectors like this. This is something which we defined last week as 1 over n, and then we had a sum from k equals 0, and in our case it's n minus 1, and then we have an x, and now we have to be a little bit careful because we are summing over the rows, k of I minus the mean value, and this is the mean value of the quantity xi, and then I had an xkj minus mu j. That was the definition of the covariance. Now we could then define a covariance matrix, which we just call for C. So remember that this is just a scalar, which you see here, right? So as a scalar, this is nothing but the two vectors multiplying with each other, right? And you can see easily now that this covariance matrix, so this is just a scalar, but we can define the covariance matrix. And this covariance matrix is something which we last week called C, and I'm just writing this as X. And you can see that this, in terms of the design matrix, so this is the design, this is a matrix, uppercase letter of X. Alternatively, you can write it in the way you will see in many statistics texts in terms of the vectors. So you would also see this as the expectation value. And now this is a lowercase letter of X times, it's written in a more compact way, of X times X transpose. So keep in mind now that the vector X, which you see, is defined like, these vectors are defined like that. So when you're calculating a matrix, you have to take the outer product. And that's why we have X times X transpose. But when I'm setting this up as a matrix, and I invite you just to check it, it's going to look like this. Now, this is an interesting property, because we know from ordinary least squares, OLS, we have the parameter beta is given by xt of x minus 1 xt times y. We know that the second derivative of the cost function of d beta t of d beta is actually equal to this Hessian matrix, and that's equal to x times t times x. Actually, this is the same derivative which we would get for Lasso and Ridge. The second derivative for the cost function for Lasso and Ridge is the same as for ordinary least squares, because Lasso and Ridge, they have only a parameter beta which comes with this lambda here. So when we take the second derivative, we actually get the same second derivatives. And that's a pretty interesting thing. So what does this have to do with the singular value decomposition? Where does that come in? So let's go back to what we did in the beginning of the lecture. So where is the SVD? So remember now that what we saw is that x times transpose times x is actually given by this v times sigma transpose times sigma times v of t. So that's the decomposition we did when we began the lecture. So let's do one thing now. Let's just multiply with the v from the right. So we multiply with the vector v. So what we have then is x, no, the matrix v. We get my times v. And this is v times sigma t times sigma. What is this? So remember now that when you do the SVD, and that's the computational price you have to pay, the SVD requires many more floating point operations than a standard diagonalization. Actually, I think it's twice as many. If you look at this expression here, so sigma t times sigma is just a diagonal matrix with singular values on it. So if you take a look here, this is given by v times this matrix, which now contains sigma 0 squared down to sigma p minus 1 squared. So what kind of equation is this? Has a famous name in linear algebra. So remember now that V has orthogonal vectors, right? So if I pick one of them, so this is the same as multiplying xt, if I take one of the vectors, times v of I, right? Remember now that I can rewrite v as a set of column vectors. This is going to be v of I times sigma I squared. What do we call this? Yeah? Eigenvalue. It's an eigenvalue problem. But we already solved it, right? So what this says is that the eigenvalues of this matrix, xt times x, which is the covariance matrix, which by accident is also the second derivative of the ordinary least square problem. It says that the eigenvalues are given by the singular values and the orthogonal vectors v of I. So if I have solved the singular value problem, I can actually find my eigenvalues of the covariance. Now, these eigenvalues are also the eigenvalues of this matrix which you have here, the Hessian. So these eigenvalues are all positive, right? So that means that x transpose times x is a positive definite matrix. So last week I claimed that x transpose times x is a positive definite matrix, and that means that for ordinary least squares, Lassell Ridge, we will always be dealing with a convex optimization problem where there is a global minimum, if the matrix is positive definite. So what we've showed here with the SVD is that the matrix is positive definite. This is another linear algebra gem. I hope I can conceal this kind of enthusiasm for the linear algebra, and hopefully it gives a little bit of this kind of deeper insight. These are small digressions, but they are very useful a little bit later when we come to principal component analysis, but also when we are going to look at important properties like the covariance and then the correlation matrix, because these are things which we use again and again and again in these type of problems. So, end of lecture today. The kind of wisdom you can extract is that we have proven that the second derivative leads to a convex matrix and a positive definite matrix. And we've linked ordinary linear regression with ridge, and we see that by tuning this parameter lambda, we can get rid of some specific features. So tomorrow we are going to look at some simple examples and run some codes, and then we are going to make the link with statistics. And next week we are going to look at resampling methods, which will be the last thing you need for project number 1. Okay, guys, thanks for your patience. Okay, cool. Okay, for those of you online, we're going to stop the recording.